How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You're in the kitchen. Dinner is on the stove. The water is boiling, you're chopping vegetables, and both of your hands are covered in olive oil and garlic. You can't touch anything. You glance at the clock and realize you need to set a timer for the pasta. 10 years ago, this would have been a frantic, messy scramble to wash your hands, dry them, and poke at a tiny screen or a microwave keypad. But today, you don't even break your rhythm. You just call out into the air. "Hey computer, set a timer for 8 minutes." And from a small speaker on the counter, a calm, impossibly neutral voice replies, 8 minutes, starting now. And that's it. The problem is solved. The transaction is seamless, invisible, and utterly magical. We have woven this magic so deeply into the fabric of our lives that we barely notice it anymore. We talk to our phones, our cars, our watches, our speakers. We ask them for the weather, to play a song, to add milk to the shopping list, to tell us the capital of Kyrgyzstan. And they just do it. It feels like a conversation. It feels like understanding. We tend to assume there's a little brain in there, a tiny consciousness that listens, comprehends, and responds, a friendly ghost in the machine. But have you ever stopped to wonder how that actually works? When the sound of your voice leaves your mouth and travels through the air to that little device, what is the journey it takes in the 2 seconds before a coherent answer comes back? What are the fundamental rules, the first principles, that allow a machine made of silicon and plastic to grasp the meaning of human language? Because behind that simple, magical exchange lies a hidden and breathtakingly complex chain of events. It's a process that spans from your kitchen counter to a server farm hundreds of miles away and back again, all in the blink of an eye. Today, we're opening the black box of the voice assistant. We're going to trace the path of a single command and uncover the layers of artificial intelligence that turn the mere vibration of air into a fulfilled request. The magic we see is a world remade by voice. It's the ability to navigate a strange city without ever taking your eyes off the road, dictating your destination to your car. It's the power to lie in bed in the dark and simply ask the air to turn off the lights. It's a lifeline for people with mobility issues, giving them control over their environment with the power of their speech alone. This technology has become an ambient utility, like electricity or running water, a conversational layer blanketing our entire digital world. It fulfills a promise that science fiction has been making for nearly a century. The dream of the conversational computer, from HAL 9000 in 2001, A Space Odyssey to the chatty shipboard computers in Star Trek, we've always imagined a future where we would talk to our machines as easily as we talk to each other. And now, in a very real way, we do. These assistants can even handle nuance. You can ask, "What's the weather like in Boston?" and then follow up with, "How about this weekend?" And it knows you're still talking about Boston. It remembers context. It feels intelligent. And because it feels so natural, we rarely, if ever, stop to consider the sheer, monumental difficulty of the problem it has solved. To understand just how monumental it is, we have to go back to a time before we could speak to our machines. A time when communicating with a computer was a brutal, unforgiving, and deeply unnatural act. For the first 50 years of computing, the burden of translation was entirely on the human. We didn't speak to computers in our language. We were forced to learn theirs. In the earliest days, this meant physically rewiring circuits or feeding the machine a stack of punch cards, where every single instruction, every single bit of data, was represented by a precise pattern of holes. A single misplaced hole could cause the entire program to fail catastrophically. There was no room for error, no space for ambiguity. Language was pure crystalline logic. Later, we developed command line interfaces. We could type words, but they had to be the exact words in the exact syntax. Type copyfile.txt to c:\docs and it might work, but type please copyfile.txt to my documents folder and the computer would respond with something like syntax error or bad command or file name. The machine had no concept of please or my documents folder. It couldn't infer your intent. It could only follow rigid, pre-programmed commands. It was like trying to communicate with a deeply intelligent, but pathologically literal-minded genie. You had to get the magic words exactly right, or the spell would fail. The core problem, the great chasm that stood between us and the dream of conversational computers, was this: human language is messy. It's ambiguous, contextual, and drenched in unspoken assumptions. The word set can mean to place an object, to establish a rule, or to become firm like jelly. The phrase "it's cool" can refer to temperature or to a subjective opinion. We navigate this beautiful chaos effortlessly, using context and shared experience. But for a machine that thinks in ones and zeros, this messiness is a nightmare. The earliest pioneers of voice recognition saw this challenge up close. In 1952, Bell Labs unveiled a machine called Audrey. It was a room-sized behemoth of vacuum tubes and relays that could, with a bit of luck, recognize a single voice speaking the digits from 0 to 9. It was a staggering achievement, but it also revealed the scale of the mountain to be climbed. If it took a whole room to recognize 10 words spoken by one person, how could you ever build a system that could understand any word spoken by anyone, in any accent? The problem seemed fundamentally intractable. The dream of a conversational computer felt like it would remain just that, a dream. So, how did we get from there to here? How did we bridge that chasm between the cold logic of the machine and the warm, messy reality of human speech? The answer, it turns out, is not by teaching the computer to understand language in the way a human does. The breakthrough came when we stopped trying to program in the rules of language and instead built a system that could learn from examples. Millions and millions of examples. Let's start by dismantling a common misconception. When you speak to your smart speaker, it can feel like the device on your counter is the one doing the thinking. It feels like that little cylinder contains the vast intelligence needed to answer your question. But it doesn't. In reality, that device is, for the most part, just a very sophisticated microphone and speaker connected to the internet. It's a portal. The real brain, the heavy-duty processing power, is located in a massive air-conditioned warehouse, possibly hundreds or even thousands of miles away, in what we call the cloud. Your simple voice command initiates a frantic, 4-part relay race that happens at the speed of light. To make this journey clear, let's use an analogy. Imagine that instead of a smart speaker, you have a team of 4 hyper-specialized human experts working for you. Let's call them the transcriber, the analyst, the runner, and the narrator. When you speak your command, you're not talking to a single entity, you're handing a task to the first member of this team. And the first step is perhaps the most difficult of all, turning the sound of your voice into written words. So, you're back in the kitchen. You say, "Hey computer, set a timer for 8 minutes. The first thing that happens is that the microphone in your device captures the sound. But what is sound? From a physics perspective, it's just a vibration, a pressure wave moving through the air. The microphone converts this pressure wave into an electrical signal, creating a digital representation of that sound wave, a waveform. If you were to look at this waveform on a screen, it would just be a jagged, continuous line. It's a chaotic squiggle of raw data. It has no inherent meaning. It's the job of our first expert, the transcriber, to tame this chaos. As soon as your device sends this snippet of audio to the cloud, it arrives at the virtual desk of the transcriber. The transcriber's task is called automatic speech recognition, or ASR. You and I know it better as speech-to-text. This is the first and arguably one of the most miraculous steps of the process. The transcriber is an AI model, a neural network that has been trained on an unimaginably vast library of audio, millions of hours of human speech from every corner of the globe in countless accents and dialects. Its first principle is to break down the complex waveform of your speech into its smallest constituent parts. In linguistics, these are called phonemes. They are the basic building blocks of spoken language. The K sound in cat, the shish sound in shoe, the ah sound in father. The English language has about 44 of them. The transcriber's AI has learned, through its immense training, to recognize the specific, telltale patterns in the waveform that correspond to each of these phonemes. It's like being a detective who specializes in sound. It sees a particular type of spike in the wave and says, "Aha, that looks like the pattern for a T sound." It sees a gentle curve and thinks, "That's characteristic of an I sound." It slices up your audio into these tiny phonetic fragments, milliseconds at a time. But a string of phonemes isn't words. The next step is to figure out how to group them. This is where the statistical power of the model comes in. The transcriber doesn't just know about sounds, it also knows about words and the probability of how they fit together. It knows that the phonemes for I and scream are much more likely to appear next to each other as ice cream than as ice cream, unless the context suggests otherwise. It analyzes the sequence of phonemes it has identified and calculates the most probable sequence of words that could have produced those sounds. It's a game of probabilities. Is it more likely you said, "set a timer" or "set a tiger"? Based on the millions of sentences it has processed before, it knows that "set a timer" is a vastly more common and probable request. So, after a fraction of a second of intense analysis, the transcriber has completed its task. It has taken the chaotic squiggle of your voice's waveform and converted it into a clean, simple string of digital text. Set a timer for 8 minutes. The first leg of the relay is complete, but the machine still has no idea what that sentence means. Now the text string is passed to the second member of our team, the analyst. The analyst's job is arguably the most crucial and the most intelligent part of the entire operation. This is the domain of natural language understanding, or NLU. The analyst has to figure out your intent. It has the raw words, but it needs to extract the meaning behind them. Think about our sentence, "set a timer for 8 minutes." A human understands this instantly, but for a machine, it's just a sequence of characters. The analyst, another specialized AI model, tackles this by breaking the problem into 2 parts: intent classification and entity extraction. First, intent classification. The analyst looks at the sentence as a whole and tries to categorize it into one of a few thousand predefined intents. It's like a sorting hat for requests. Is this a play music intent, a get weather intent, a tell joke intent? Based on its training, it has learned that sentences containing words like set, timer, and a duration are almost always associated with the set timer intent. It sees the pattern and confidently classifies your request. So step 1, it knows what you want to do. But that's not enough. It also needs to know the specific details. This brings us to the second part, entity extraction. The analyst scans the sentence again, this time looking for the key pieces of information, the entities that are necessary to fulfill the set timer intent. What entities does setting a timer require? At a minimum, it needs a duration. The analyst's model has been trained to recognize and tag words and phrases that represent specific types of data. It sees the words 8 minutes and tags them as a duration entity. If you had said, "Set an alarm for 7 a.m., it would have found 7 a.m. and tagged it as a time entity. If you'd said, "Set a pasta timer," it might have tagged pasta as a label entity. So, at the end of the analyst's work, something magical has happened. The messy, ambiguous human sentence has been transformed into something a computer can understand perfectly. It's been converted into structured data. It looks something like this: intent, set timer, entities, duration equals 8 minutes. There is no ambiguity here. It's a clean, logical, actionable command. The analyst has successfully bridged the gap between human language and machine logic. It has found the meaning hidden in the words. The second leg of the relay is done. Now, the structured command is handed off to the third member of the team, the runner. The runner's job is, compared to the first two, relatively simple. It's less about complex AI and more about straightforward, old-fashioned programming. The runner is a dispatcher. It takes the structured command from the analyst and routes it to the correct software to get the job done. Since the intent was set timer, the runner knows exactly which application to talk to. The clock or timer app that lives within the smart speaker's software ecosystem. It takes the duration entity, 8 minutes, and passes it to that application using a perfectly formatted command that the app understands. It's the digital equivalent of filling out a form. The timer app receives the instruction and starts counting down. Mission accomplished. If your request had been different, the runner would have acted differently. If the intent was get weather, the runner would have taken the location entity, Belmont, and sent a query to an external weather service through something called an API, an application programming interface. It would be like sending a perfectly formatted telegram to the weather company asking for the data for Belmont. If the intent was play music, the runner would have queried a music service API with the artist name and song title entities. The runner is the bridge between understanding the request and actually doing something about it. Once the action is complete, the runner gets a confirmation back. In our case, the timer app confirms, timer successfully set for 8 minutes. But the system can't just know this internally. It needs to tell you. The job isn't finished until you, the user, know that your request has been heard and acted upon. The final leg of the relay begins. The confirmation message, timer successfully set for 8 minutes, is handed to the final member of our team, the narrator. The narrator's job is the mirror image of the transcriber's. It has to take a string of text and turn it back into sound. This is the process of text-to-speech, or TTS. In the early days of talking computers, this was done in a very clunky way. A system might have recordings of a human speaking individual words, and it would stitch them together. The result was a robotic, disjointed voice that we all recognize from old sci-fi movies. Your call is very important to us. Every word had the same pitch and inflection, regardless of the context. But modern voice assistants don't work that way. The voice you hear is not a series of stitched-together recordings. It's generated from scratch by another powerful AI model. The narrator is a generative model. It has been trained on thousands of hours of a single voice actor reading text, and it has learned the incredibly subtle rules of human speech. The rhythm, the pitch, the intonation, the way a voice rises at the end of a question and falls at the end of a statement. The narrator's model takes the input text, 8 minutes, starting now, and it doesn't just convert letters to sounds. It generates a brand new waveform from the ground up. It predicts what a human voice would sound like, millisecond by millisecond, as it spoke that phrase. This is why modern assistants sound so natural. They can place emphasis on the right words. They can sound conversational. The narrator generates this audio file and sends it from the cloud server all the way back to your kitchen. The small speaker on your counter receives the audio file and plays it. A calm voice says, 8 minutes, starting now. And the entire round trip, from your voice hitting the microphone, being sent to the cloud, transcribed, analyzed, acted upon, and converted back into a spoken response, takes, on average, less than 2 seconds. It is a symphony of distributed computing and artificial intelligence, a silent, invisible dance of data happening at a scale and speed that is almost impossible to comprehend. And it all happens just so you don't have to get garlic on your microwave. Now, we've walked through the whole process, from sound to text, text to meaning, meaning to action, and action back to sound. It seems like a complete picture, but there's a piece of the puzzle we skipped over, a critical component that makes the entire system possible. It's an unseen giant working silently in the background, and without it, the whole magical experience would collapse under its own weight and potentially create a privacy nightmare. Let's go back to the very beginning. You're in your kitchen. You say, "Hey, computer," and then you make your request. We focused on what happens after you say the wake word. But what about before? Is your smart speaker constantly recording everything you say 24 hours a day, sending a continuous audio stream to the cloud for the transcriber to analyze? If you think about it, that would be the only way for the cloud server to know when you've said the magic words. But this would be a terrible solution. First, it would be a privacy disaster. It would mean that every conversation you have in your home, every whisper, every argument, every private moment, would be sent to a server owned by a massive tech company. Nobody wants that. Second, it would be an engineering catastrophe. The amount of data generated by constantly streaming audio from hundreds of millions of devices would be astronomical. It would clog the internet and require an absurd amount of processing power. So, this isn't what happens. The system needs a way to listen without really listening, and the solution is the true first principle of how these devices work, the wake word engine. The unseen giant is a tiny, hyper-efficient, and completely offline artificial intelligence model that lives directly on your local device. It is not in the cloud. This little AI has been trained to do one thing and one thing only, to recognize the specific sound pattern of its wake word. Hey, computer, Alexa, OK, Google, Siri. Think of it like a guard dog sleeping at the door. It's not paying attention to the content of the conversations happening in the house. It's not trying to understand words or meaning. It is physiologically tuned to perk its ears up at only one very specific sound, the sound of its own name. Most of the time, the device is in this low-power, sleeping state. The microphone is technically active, but it's feeding a short, constantly overriding audio buffer, just a few seconds long, directly into this tiny local wake word model, and nowhere else. The model analyzes the sound, and if it's not the wake word, the audio is immediately discarded forever. It never leaves the device. But when you say, "Hey, computer," the waveform of your speech creates a pattern that this little model has been trained to recognize. It's a match. The sleeping guard dog wakes up. A signal is triggered inside the device. Now, and only now, does the device open the floodgates. It begins recording the audio that follows the wake word and sends that small, specific clip. Set a timer for 8 minutes on its journey to the big, powerful AI brains in the cloud. This is the profound and often misunderstood genius of the system. The complex, power-hungry, and potentially privacy-invasive work is only done when it's explicitly requested. The constant listening is done by a simple, dumb, and secure process that acts as a gatekeeper. This principle of local, on-the-edge processing for the wake word is what makes the entire architecture of voice assistants feasible, efficient, and acceptable to have in our homes. It's the handshake protocol that initiates the whole symphony. Without this tiny sleeping guard, the magic show couldn't even begin. So let's retrace our steps. We started with a moment of effortless, almost magical convenience. A voice in the air, a task completed. It feels like a conversation with a single intelligent entity, but when we broke it down from first principles, we found something entirely different. We found a distributed four-part assembly line, a relay race between highly specialized ICE. First, the transcriber, a phonetic detective, which takes the raw energy of sound and painstakingly deciphers the most probable sequence of words. Then, the analyst, a master of intent, which ignores the poetry of our language and instead distills our messy sentences down to cold, structured, actionable commands. Then the runner, a simple dispatcher, which takes that command and routes it to the right software to get the job done. And finally, the narrator, a generative artist which doesn't just read words back to us, but creates a new human-sounding voice from scratch to deliver the reply. And we learned that this entire complex symphony is only conducted after a tiny local gatekeeper. The wake word model hears its name and grants permission for the show to begin. Understanding this process changes how we see these devices. The magic of a thinking machine is replaced by the reality of a statistical prediction engine. The assistant isn't understanding your request in a human sense. It's making a highly educated guess based on patterns it has seen millions of times before. It's less about consciousness and more about incredibly powerful, incredibly fast pattern matching. And yet, in a way, the reality is more impressive than the illusion. It teaches us something fundamental about how complex problems are solved in the modern world, not with one giant, monolithic brain, but with a system of smaller, specialized components, each mastering one piece of the puzzle and working together in perfect coordination. The dream of artificial intelligence wasn't realized by creating a machine that thinks like a human, but by creating a system that deconstructs a human problem into a series of machine-solvable tasks. By replacing the magic with mechanics, we don't lose the wonder. We find a new appreciation for the ingenuity of the system itself. We see that the greatest leap forward wasn't teaching a computer our language, but rather creating a universal translator that could finally bridge the gap between our world of nuance and intent and its world of logic and code.
You've been listening to First Principles. Until next time, stay curious.